Thank you, Ludmil. It's a great pleasure to be here at the University of Miami. I've been here in Florida for 7 years, and I haven't been traveling much here. I have visited Florida Institute of Technology, and I think that's it. That's it. So very happy to be here, and happy birthday, Steve. All the best for you. Good. So this I designed this talk for a no-expert audience. This is what I'd like to talk about today. I will just be revising mostly of the time, revising the classical theory. I will explain about the structure, the universal structure of free-bounded problems, and the difficulties on when you try to grow away from this universal structure. And then I will tell you towards the end some new results that we were able to obtain. And okay, so let me explain the classical theory. Okay, so again, I'm not assuming any previous knowledge on PDEs or free-bounded problems. This has to do with the over-the-term system of PDEs. So the problem goes like this: your first PDE course, you fix a nice bounded domain omega, and you give a function L in L2, right? So we know that you can always solve this problem. Okay, this is the first PDE course. By variational methods, you always solve this problem, and the solution is unique, right? So it's a nice problem, it's a nice result. We are all happy about this result. So another way of interpreting this is that these, let's say, boundary to Neumann operator, so that takes a function, let's say a Hilbert continuous function on the boundary f, solves the equation and computes the normal derivative of the equation, is well defined, right? So in harmonic analysis, they study this operator. They study this operator a lot. It's well defined. So it seems to be a good news in terms of harmonic analysis point of view, because this equation is well defined. Again, this operator, you give me a function f, I solve the equation, and the potential associated to f, I compute the normal derivative is still going to be a Hilbert continuous function by regularity. That's a well-defined function. But I'm going to switch the perspective of this good news in a slightly different way. I'm going to put it differently. I'm going to say the following. For these kind of problems, if you select the Dirichlet data, you don't get to pick the Neumann one, right? It's completely determined. Everything is completely determined. Okay, so that's life. But what happens if you really want or need to prescribe both? Okay? And there are situations in mathematical physics that you really need to do that. And one of them is called the cavitation problem. So in cavity problems, you want to find a function which is, let's say, harmonic in a region of positivity, vanishes somewhere, but you also want to prescribe precisely the angle that it vanishes, right? It's the constant normal derivative in some particular cases, right? So you see, I'm not only requesting a Dirichlet condition to vanish, but also I'm trying to describe the Neumann condition. So to approach this kind of problem, you need to change the perspective. Instead of asking if you can do that, the change of perspective is the following. Given a target function, let's say f and g, the question should be, is there a, let's say, as nice as possible domain such that this over-the-term problem can be solved? So you see that now the problem is much harder, because it's not that you're looking for a solution, you're looking for a domain that supports the problem that you're trying to solve. Okay? And that's why this is a free-bounded problem. The unknown is not the solution per se, but actually the boundary of the set. Okay? So this is what I just said. Okay? And this is a very important problem. It appears a lot in mathematical physics, and there has been a lot of work on this thing. But mathematically, we will only be able to approach this problem in a well, let's say, structured way in the early 1980s. Right, a very famous paper of Alta and Caffarelli. What they did was they showed that if you minimize this functional, which is like directly a classical directly energy plus a function q times the characteristic where u is positive. And here you notice that the characteristic where u is positive is a non-differentiable function, which is going to create a lot of difficulties in the analysis. So what they showed is that there exists a minimizer. Minimizers are harmonic in the set of positivity. They are Lipschitz continuous, only Lipschitz continuous, and this is the optimal regularity. And then they investigated the boundary of the region where u is positive and showed that this is a smooth surface up to a negligible set. And in fact, if you solve this equation, it's equivalent to solving the Bernoulli, the overdetermined free-bounded problem. So a minimizer of this equation satisfies everything that you want, and the normal derivative is q. So you give me q, I solve this equation with the happens. And the equation, the Neumann condition is satisfied as classical as possible. There might be some singularities on this thing, which has to do with the theory of geometric measure theory pertaining to minimal surfaces. So I would like to highlight that this condition, that q is bounded away from 0 and infinity, is absolutely critical from the page 1 to the page 45, which is something around that. So every single page of the paper, this condition is used in a very fundamental way. It's more than only mathematical. It's not only a technical condition. It's fundamentally used that q. So in other words, the angle that you are prescribing on your physical problem is positive away from 0 and infinity. And I would like to highlight that.
What is this phi in the appendix of the circular space?
It's just a boundary condition. So you have omega, which is that's omega. So you fix a boundary condition, and then you try to solve the cavity problem inside. Right? So take phi equals 1, which is completely fine. Okay. So let me kind of do a summary of the scientific endeavors since it's one of, I think this is probably one of the papers of Caffarelli that has more citations. Certainly one of the 5 that has more citations. It has really created a school around these kind of problems. There are many extraordinary good people that have made careers out of this paper. It would be impossible for me to list everything that has been done since this foundational paper, but what I'd like to highlight is that these free-bounded problems lead to discontinuous functionals or singular perturbidities. This has to do with some non-variation approach of the problem that you can also set up. It has been done in the 90s. There exists like a huge number of works on similar free-bounded problem with, let's say, different operators. So for instance, if you change the Laplacian to the P Laplacian, then it becomes a completely different path of research. But I'm not saying that they are easy problems. They are extremely difficult problems. There are a lot of technicalities that that come along with changing the operators. But they always keep the same structure. In other words, this condition that the angle is positive and bounded away from 0 and infinity is in all problems that I have mentioned. So in particular, it's critical, let me say that the Q, the angle, the Neumann condition is comparable to 1, let's say, is absolutely critical in all these problems, with the exception of just one. In a little bit more than 10 years ago, there's a very important paper by Barbara Kura and George Weiss that broke this protocol. And I'll explain this, what they did. So this has to do with the geometric approach to the Stokes conjecture. So what they were able to prove in this paper was that if they investigate the minimizers of this functional, this is equivalent to solve. So the Stokes conjecture has already been solved. This has to do with fluid mechanics, and the problem has already been solved. But what the importance of these papers that they provide a different, a more geometric approach to this using the Alt-Caforelli kind of techniques. They basically show that minimizing this function is equivalent to solving the Stokes conjecture. And but I would like to highlight that to be able to do that, they had to allow this function Q that appeared in the Alt-Caforelli functional to vanish. So it's no longer a bounded away from 0 and infinity. And this connects them to the Stokes conjecture. Okay. And the key observation is the following: the free boundary points lie on this hyperplane. What they observed is that a superior regularity is noted. So if I'm not mistaken, they proved that, so Lipschitz regularity is the optimal regularity for the obstacle, for these cavitation problems. But here, for this problem, what they were able to show is that for free boundary points, their solutions are C1 1/2, if I'm not mistaken. C1 1/2. It's written there. It's 3/2. I don't see because of. Okay, good. So what we did, that's a project that started maybe 4 years ago with a colleague from Florida Institute of Technology. And I'll explain. So what we decided to do is, okay, let's try to reverse the thing. What happens if instead of vanishing the Neumann condition, vanishing, what happens if it blows up? Okay. So we had some motivations to do that. The first one is cavitation problems with perpendicular incisions. So maybe you wanted to create a cavity that really hits the floor with a perpendicular condition. Right? So to be able to do that, I need so the Neumann condition will be infinity. So there are other motivations that appear from let's say melting ice. So maybe you have a melting ice and you have something that is holding the ice. So when you set up the problem, you can also, there are some interpretations of this problem that is involved with this melting ice thing. So the flux on this grid will have to be, because the grid is not melting with the ice. So there will be some regions, which in this case is fixed. Maybe it melts along with the ice, where the latent heat to be able to melt would theoretically be infinity because it's not melting. So somehow you would be able to, you would have to include situations where there are some points, some part of the free boundary that has the latent heat to be included. So mathematically is not a big deal. Mathematically, we knew from the beginning what what should be the setup of the problem. Mathematically, what we are interested in is minimizers of this kind of energy functionals. We introduce a bounded measurable coefficient a of x, which has to do with heterogeneity of the beam. But the key novelty is to include as, let's say, the cavitation functional, a function phi that is just in LQ or LQ weak. So there will be some points where it becomes infinite. And I'd like to understand what happens on free bounded points where phi goes up. So a few remarks, because a harmonic function, this has to do with the George Nash-Moser regularity theory. Solutions of this equation are only Hilbert continuous. That's a well-known fact. So even these a of x, they will beat a maximum regularity for this function. And solutions of this Poisson equation, even if a is the Laplacian, also has much less regularity because of y is in L. So this is also comes from potential theory. So it is expected that minimizers of this functional will have less regularity than the original one, which is Lipschitz. But the problem is a little bit more involved because, in fact, if I just say that solutions are some particular regularity, I'm not telling you the whole story. Because if I define for let's say gamma to be the Bernoulli, the region where you is positive, then I can extract gamma as being in two parts. There's some, let's say, gamma star and gamma infinity. Gamma star is the region where gamma meets the as Neumann conditions finite, right? And gamma infinity is where the free boundary meets the region where phi blows up, right? For all those points, the classical theory should hold, right? Nonetheless, it is a local thing because you localize, you can. It is a local property. So as long as phi becomes finite in a region, in an open vault around a free boundary point, every tool that it's available in the literature, you can just import. Those are the troublemakers. But this is not the whole story, and we were having Ludmil, Ernest, and I were having a very interesting discussion today about calculus students, and this is the first thing that we attempt to teach our calculus students is that infinity is not a number, right? Infinity is a concept. And if I just say that thing is infinity, I'm not telling you much information. You cannot do much with this information. If I say it's 2, it's 2, done. If it's 15, it's 15, done. If I say it's infinity, I'm not giving you enough information to do much with this. So in fact, for those points, I must do yet another stratification to be able to capture what this infinity really means. And that was a very tough, when we started this project, we had no idea what that means. We knew that some further information would be required, but we had no idea whatsoever what we would need to be able to, so what would be the mathematical manifestation of this fact that infinity is not equal all the time in this particular geometric problem. So that's what I'm saying. So for all those points, so we had clear in our mind that for those points, the free boundary should develop cusps. Those cusps, the geometry of those cusps should be related to how abrupt the phi blows up at those points, all those kind of things, we had like a feeling that that could happen, but it was absolutely not clear whatsoever how we would relate some analytical properties of phi with this geometric manifestation on the free boundary. Okay, so first things first, we need a compactness result. So this is Stanley Nelson, is a professor, assistant professor at the Florida Institute of Technology. So the first thing that we were able to prove is that the solutions are Hilbert continuous, so the minimizers are Hilbert continuous. And we have this, so this alpha naught is the alpha that comes from the George Nash-Moser theory, and this is related to phi, to the Neumann condition. So notice that when Q goes to infinity, this vanishes, I get 1. So if my operator, let's say, have Lipschitz norms, so this would be a Lipschitz regularity. This is a local property, so it's a local regularity. And as I said, I'm not telling you if I just give you, so strategy of the proof, I'm not going to bother. It's kind of an interesting proof because to some extent it gives you a it gives you a different approach to obtain regularity in the calculus of variation that uses some known tools, but also uses some tweaks that has been proven to be very powerful in problems that you cannot use techniques that are available at this point. So, but I don't want to bother you with this strategy. But here comes a very interesting result. That when we were able to prove this result, we were saying, okay, we are hitting something here. So the problem that we proved was the following: is that if you are in a pre-bounded point, then U behaves as a distance to the 1 minus d divided by 2q, regardless of the heterogeneity of the medium. So regardless of the alpha regularity that comes from the George Nash-Moser theory. So that was that was a very interesting result, because basically what this result is saying is that the free boundary for those particular points, the free boundary disregard the heterogeneity of the medium, and it shape itself in a way as to accommodate the strength of the Neumann condition that you are imposing. I'm not going to bother you with the strategy to prove. This is a much more complicated proof that required several new ideas that took us a good year to come up with.
But why did you expect that kind of limitation was true?
It's counterintuitive actually, because in free boundary, the free boundary is where things go bad, right? So somehow on those free boundary points, the solution might behave better than the what is imposed by the heterogeneity of the medium, right? In all fairness, I do have a previous result pointing towards this kind of phenomena, but not in this context. Okay, so now let me explain the main result that we were able to prove, which has to do with this classification of infinities, right? So the goal now is to, so imagine that so now imagine that someone solved the cavitation problem. I don't have access to phi. I just have access to the drawing that he did to be able to find the free boundary. And the question is, how can I reverse engineer, or in other words, to recover the Neumann condition just by looking at the cusps on the free boundary? Okay? So the picture goes like this. Oh, there's something there. Okay, so take a free boundary point where you have a cusp. So if you have a cusp, it's because phi, the function phi, the Neumann condition blew up here. So those are points that I can analyze using classical theory, and this is a point that is developing a cusp, phi blew up here. Right. So if I take a ball centered at Z naught, okay, and this is a phi, so phi is blowing up at Z naught, okay. So I have an analytic description. So if phi, when I say that phi is in some LQ1, let's say Q1 space, what I'm telling you is that I'm giving you a upper bound on the velocity that phi can blow up, right? So phi cannot blow up very, very fast, right? So to be able to prescribe what's this geometry, I not only need a condition on how fast phi blows up, but also a condition that was absolutely critical in our analysis. I also need a condition that tells me that a minimum speed in which phi blows up. And we created examples showing that. So the theorem that we prove is that under this condition, so if I have a condition, if I tell you that phi blows up at a maximum rate and a minimum rate, then I create these two numbers, phi1, which is the optimal regularity that we were able to prove, which is a Hilbert continuum regularity. And I define alpha2 to be this number, which corresponds to the other Hilbert regularity condition. These numbers don't have to match. So we were able to prove that there exists a universal constant that depends only on dimension and ellipticity, such that these two things happen. So if the volume of the region where U is positive, intersection with the ball of radius r, divided by the total volume of the ball to this particular power, is bounded universally. It doesn't depend on r. So if you keep zooming in, you always have a portion of this ball in this region, and also to the other side. And P of Q and Q minus and Q plus is given by this algebraic expression. So, so this is really telling me that so if you think like this is a clever way of classifying the cusps. So cusps, if you think about cusps, they are like the graph of a function absolute value of x to some power. I could give this, which in my case would be hard, but what I could also give you is the density of the vertex. And this is what I'm giving is the not only from inside and from outside. So this guy is equal to alpha 2 divided by alpha 1 if and only if q plus equal q1. So as a corollary, what we were able to prove is that if the Neumann condition blows up in a steady race, so if it's an L, is a genuine, let me put this way, it's a genuine LQ function, so it really blows up with the maximum speed that an LQ function is expected to blow up, then there is no cusp, because this becomes 1 and this becomes 1. So it is a differentiable point. And if there is a deviation from these speeds, then it creates the cusps. And more than that, it classifies the cusps. Right? So it classifies the cusps. So this is the ultimate conclusion, is that the free boundary will always develop cusps with a precise severity. So we can classify the severity of the cusp unless phi blows up at a precise state. And with this, I'll stop.
Okay, thank you very much. Questions?
Yeah, just some curiosity because I have not much experience with this boundary problems. But like, suppose that you like want to find these functions on the boundary, but let's say that you want your boundary to be stratified as somehow like by levels where your function is constant like along some region. You see what I mean? Like,
yes.
Would that be fitable scenario for boundary problems?
Well, it reminds me a result. I'm not quite sure in these kind of problems because they are a little bit more singular. But in the obstacle problem, what you described is a major paper by Caffarelli from the beginning of the 1980s. Also, it's a completely different one. Is that he was able to show, so in the obstacle problem, which is a free-boundary problem which is more regular than this one. But in free-boundary problem, in the obstacle problem, what Caffarelli was able to prove is that there are regular points and singular points. For regular points, the free boundary is real analytic, and for the singular points, you can stratify them using the range, the rank of the bilinear transformation that is associated with the point. With fixed rank, you can find a C1 submanifold that contains them all within the free boundary. So they are like points that are dispersed on the free boundary, but it's not that they form a C1 surface, but there exists a C1 surface that will collect them all if you fix the rank. So it would be very interesting to see if something similar to that could be proved here. So, for instance, now take all those points, the cusps, and try to prove that there exists a C1 manifold that collects all the ones with a prescribed severity. That would be a very interesting problem. It's a good suggestion.
So there are techniques of analyzing some singularity of real surfaces by Georgia and this company that come. So how do their techniques relate to what you're doing?
So it's a good question. The George proves Hilder regularity for solutions, weak solutions of a given PD, and of Nash and Moser, right? If you go to the calculus of variations, minimizers of the corresponding energy functional satisfies a Euler-Lagrange equation in the sense, right? So you could use the George to obtain that. But for what we were doing, these direct methods from the calculus of variation cannot be applied because you don't get a PDE back because the functional is not differentiable unless you force a little bit and you treat PDEs with the right-hand side as a measure. But in this case, the measure is not a pointwise measure. The measure acts as a function. It's a much more complicated thing. So even if you don't have a heterogeneous median, the Euler-Lagrange equation associated to it would be Laplacian of u equals the Dirac mass at u. So you would have the Dirac mass as a functional acting on you. I don't know if it's possible to carry out a similarity, but maybe for didactical reasons, that's not what were done. And what, going back to your question, what we were able to do here offers a universal approach to all these kind of problems. So if you, for instance, if you want to write a didactical book proving the George, you can take this, project properly, and you would have, let's say, a new proof of the George. Which is not quite fair because I mean, the George did that 70 years ago with much less knowledge, right? So I'm importing many of his insights and tools and giving back to him what he did. But yes, that would give a universal approach for these kind of results.
Other questions?
Is it so? Since I'm not really familiar, but is it always that the minimizer has the gradient of u? Like I'm more interested if there is, instead of the gradient, the different like Laplacian, like for example in the Hamiltonian, I mean depending on what PD is, it can be higher, right? Like
yes, exactly. So if you put the Laplacian, then the automatic equation is going to be a fourth order,
exactly,
right?
like a biharmonic and a less
biharmonic, yeah. There are results on these things. The problem with putting the Laplacian is that you lose one tool, which is critical, which is the maximum principle is not available anymore. So, but people have done that. Yes.
All right, let's thank Eduardo.